Welcome to Module 2, Classical Mechanics, focusing on Newton's laws of motion. These fundamental principles, established by Sir Isaac Newton in his 1687 work, Principia Mathematica, form the foundation of modern physics and mechanical understanding. Our journey will cover an introduction to Newtonian mechanics, followed by a deep dive into each of Newton's three laws: inertia, F equals ma, and action-reaction. We will finish with practical applications, problem-solving, and a summary of key takeaways. In 1687, Newton published his laws, providing a unified framework for mechanics. These principles govern all classical motion, enabling the Industrial Revolution and space exploration. Even with advances like relativity, Newton's three fundamental laws remain essential tools for science and engineering. Newton's first law, the law of inertia, states that an object resists changes to its motion unless acted upon by a net external force. Mass measures inertia, meaning more massive objects have greater resistance to changes in motion. This explains why your body lurches forward when a car brakes. Newton's second law defines the relationship between force, mass, and acceleration. F equals ma. This mathematical foundation shows that acceleration is directly proportional to the net force and inversely proportional to the mass. Force and acceleration are vectors, always pointing in the same direction. Newton's third law is the law of action and reaction. It states that for every action force, there is an equal and opposite reaction force. Crucially, these forces act on different objects and therefore never cancel out. This principle explains propulsion in rockets and how we walk or swim. To solve problems, we use free body diagrams, or FBDs, to visualize forces. The process involves drawing the object as a point, identifying and drawing all force vectors, and then finding the net force and acceleration using F equals ma. This tool is essential for applying the laws correctly. When solving problems, follow a structured strategy. Read the problem, draw an FBD, choose a coordinate system, and apply Newton's laws. For instance, a 10-kilogram box with a 20 Newton net force accelerates at 2 meters per second squared. Newton's laws have vast real-world applications. Automotive safety relies on them to design crumple zones and seatbelts. They govern sports dynamics, such as the force and time needed for a powerful kick. They are also fundamental to space exploration and the design of engineering marvels like bridges. Be aware of common misconceptions. Remember that force is only needed to change motion, not to keep an object moving. In a vacuum, all objects fall at the same rate, regardless of mass. Finally, action and reaction forces never cancel because they act on different objects. In summary, the first law covers inertia, the second law gives us the quantification F equals ma, and the third law explains how forces come in pairs. These three laws are interconnected, providing a complete framework for classical mechanics. Mastering FBDs is key to applying them. You have now mastered Newton's laws and possess the fundamental tools to analyze and predict motion. These principles are the gateway to understanding energy, momentum, and advanced physics. Keep practicing, keep observing, and remember that physics is a way of explaining the world.